Hi, I'm Alex Chrysanthemum, and in this video I'm going to tell you about the simulation of a 16-bit ALU, or arithmetic logical unit, that I wrote in Verilog code. So here at the top we have defined a module for full adder, and this is similar for all small hardware components in the ALU. We start them all with the module, give them their own module, and you can see in this full adder module, we have the inputs are A, B, and C, and outputs are S and C out. One output for the sum of the two values A and B, and then one value C out for the possible carry out bit that can occur in addition. If we get something like 1 plus 1, that means we have to carry out another 1, which is also stands in for our C carry in. Then we also have an XOR gate over here, an AND gate, and another OR gate. These are all things we need to create the full adder itself. So similarly, below we have a module for a 2x1 mux. You can see that it takes in two characters, 2 bits, A and B, and it also has a select bit since it is a multiplexer. Same thing here for the 4x1. We have A, B, C, D, and 2 select values. They both have one output as well. And then we get here to the 1-bit ALU. So here is where some of the magic starts to happen. We have the AND gate here. This will AND the two A and B values. Then we have an OR gate here. So this will OR the two bits and give an output as OR out. And then we have a NOT gate here. You can simply just negate the value. And then we have a 2x1 mux. So what this 2x1 mux does is it takes in the opcode. So the opcode is a string that we'll talk about in a few minutes later in the video. That basically tells the ALU what operation to perform. So it should be either AND, it should perform the AND uh, evaluation, it should perform the OR evaluation, or it can add, and it can also set on less than, which we'll talk about later as well. So here's the 16-bit ALU. This is comprised of 16 1-bit ALUs. And so what happens is each bit in the input string will come into one ALU. We'll come to the first 1-bit ALU, and then the second two bits will come into the second ALU, and so on. And this way we can trickle down all the carry-ins and carry-outs so that we get one final answer with our ALU. So let's take a look at another file here that I have. Okay, so this is our input file here. We have all the testing is done over here in this initial statement. So we have a hashtag 10 nanosecond delay before each input gets processed. Here we have our two input values, A and B. A is going to be equal to 90 and B is going to be equal to 100. Then we have our opcode here. Each opcode represents a different operation that will be performed on each input set. So here we have all 0, 0, 0. That means all these, since all the opcodes are set to 0, are going to be AND testing. These will be same numbers. I gave it the same values just so we could see. And 0, 0, 1 is going to stand for OR testing. And then we'll have testing for add operation, testing for subtract operation, and testing for set on less than. And that'll basically just tell us is A less than B. Yeah, so that's basically this file. We just have a bunch of inputs here, and the next thing we can do is just run the program and see what happens. Okay, so here we have access to our terminal through PuTTY, and we're going to run the program. Just remember quickly that we have these 4 sets of values here. A equals 90, B equals 100, A equals 56, B equals 25, A equals 3, B equals 5, A equals 50, and B equals 33. we're going to be using this four set of numbers for each operation now. So we're going to do those four set of numbers, perform logical and, perform logical OR on them, we'll perform add on them, subtract on them, and we'll check if value of A is less than the value of B. So here we go. Run this VVP, and the file is called ALU _0. So here you can see at the 0 part, the 0 line. This just means from 0 time. We have XXX says value A and B, XXX for everything. These are just the initial garbage values that are in our registers. We can basically just disregard them. It's just to show what happens when the program first runs. So once we get to 10 nanoseconds in, we have our number. We have our number here, our string for A, and this will be 90. And this B value over here is going to be equal to 100. You can double check those if you'd like. And then we'll go and perform the operation. So the opcode here, which stands for basically the operation that we'll perform, is 0, 0, 0. Therefore, we're performing an AND, logical AND. So if you see here, if you're counting 0, 1, 2, 3, 4, 5, 6, this will be the sixth index. It's 1, 1, 2, 0, 1, 2, 3, 4, 5. And the sixth index here is also 1. So if we do logical 1 with if we add logical AND 1 and 1, we'll get the output of 1 in the sixth index. So we have 0, 1, 2, 3, 4, 5, 6. That is correct here. So and then it'll do it for each bit in the index. So this will be the final output for 90, logical and 100. And we can do that. You could double check the rest of the answers if you'd like, but I'm positive that they'll work. But yeah, so that's basically it, and hope you enjoyed, and see you next time.